Welcome students, welcome to the video class. Today we are going to discuss a topic that is force on a charged particle when it is placed in a uniform magnetic field. Again, जदि गोटे चार्ज पार्टिकल मैग्नेटिक फील्ड रखिबा तापरे कोन इफेक्ट पड़िबो. This is today's topic. Okay, before moving to that, हम माने टिके पछ क्लास रो direction टिके रिवाइज करिबा. The direction of magnetic field produced by a current carrying conductor. Okay, we know that a current carrying conductor produces magnetic field. If I say this is the current carrying conductor, the magnetic field is circular in nature, that is either clockwise or anti-clockwise. Okay, so if I say this is the current carrying conductor, then यदि हम ए जगह मैग्नेटिक फील्ड बाहर करिबा, the thumb represents the direction of current, finger represents जो जगह रे बाहर करियो magnetic field, and the direction of the palm represents the direction of magnetic field, that is inward. तो ए जगह रे magnetic field हबो inward, ए जगह it is outward. Or you can say if this is the current carrying conductor, the magnetic field is anti-clockwise. तो ए जगह रे inward, ए जगह रे outward. Okay. Similarly, जदि गोटे circular current carrying conductor थिबो, the magnetic field is straight, that is along the axis of the circular current carrying conductor. Jadi suppose if the current is moving in anti-clockwise direction, the direction of magnetic field is straight, that is up, that is along the axis of the circular current carrying conductor. Similarly, if the current carrying conductor or that current is clockwise like this, the direction of magnetic field is downward along the axis of the circular current carrying conductor. Okay, next we'll move to our topic or today's topic, that is force on a charged particle placed in a uniform magnetic field. Okay, so it was Dutch scientist Hendrik Anton Lorentz who first recognized that certain force act on a charged particle when it is placed in a uniform magnetic field. Okay, suppose let us consider a charged particle Q which is placed at rest in a uniform magnetic field B. In that case, it experiences no effect. But whenever a charged particle Q is allowed to move with a velocity, it experiences a deflection. So let us consider a positive charge plus Q allowed to move with a velocity. Then it experiences a deflection like this. So since it experiences a deflection, the deflection must be due to some force. We call this force magnetic force. Again, whenever a positive charged particle is allowed to move with velocity in a uniform magnetic field, it experiences a deflection, and this deflection must be due to some force. We call this force magnetic force. But whenever a negative charged particle is allowed to move with velocity, in that case the deflection is opposite to the direction of positive charge. Okay, from all this we can conclude that whenever a charged particle is placed at rest in a uniform magnetic field, it experiences no force. But whenever a charged particle is allowed to move with velocity, it experiences a magnetic force. And third is the direction of magnetic force on the negative charged particle is opposite to the direction of magnetic force on the positive charge. Okay. Next we will move. Next we will find the magnitude of magnetic force and its direction. Okay. Let us consider a positive charge Q moving with velocity v in a uniform magnetic field B along y-axis. Let that velocity v makes an angle theta with the magnetic field. We can break the velocity v into its rectangular components. Okay, it will have two rectangular components. One is v sine theta and second is v cos theta. V cos theta will be along magnetic field, v sine theta will be along x axis. Okay, from the experiment it is found that the magnetic force on the charged particle F is proportional to the magnitude of charge Q. It is also proportional to the magnitude of magnetic field B. The force is also proportional to the perpendicular component of velocity, that is v sine theta. Okay, from the above condition we can write F is proportional to, that is Q B v sine theta. Proportional उठे गोटे constant आसियो, तो F is equal to K Q V B sine theta. The magnetic force is chosen in such a way that the value of the constant is unity, that is 1. So we can write F is equal to Q V B sine theta. Okay, we can say when a charged particle Q moves with velocity v in a uniform magnetic field B, then it experiences a force which is given by F is equal to Q V B sine theta. This magnetic force depends on the magnitude of charge. It also depends on the velocity of the charge. It also depends on the magnitude of magnetic field. It also depends on the angle between the velocity and the magnetic field. Okay. Again, we know that A cross B is equal to AB sine theta. Okay, in vector, we know that A cross B is equal to AB sine theta. So here, F is equal to QVB sine theta. So we can write in vector form the magnetic force F as F is equal to QV cross B. So in vector form, we can write the magnetic force as F is equal to QV cross B. Again, we know if A and B are the two vectors and theta is the angle between them and R is the resultant of A cross B, then we can write R is equal to A cross B. Okay, what is the direction of the resultant force? Okay, we know screw rule. From the screw rule, we can say that if you move from A to B यदि हम A to B move करिबा like this, the direction of the screw gives the direction of the resultant, so it will be along this direction like this, A to B, like, or we can say the direction of resultant is perpendicular to the plane containing A and B. Similarly, here the magnetic force is equal to QV cross B. So it is a cross product. The force must be perpendicular to the plane containing the velocity and the magnetic field, which is shown in this figure. So if you move from V to B, the direction of force is perpendicular to the plane containing V and B. Next we will move to the special cases of the magnetic force F. Okay, special cases. Case 1. We know that F is equal to QVB sin theta, or F vector is equal to QV cross B vector. If Q is a neutral particle means I will say this charge is equal to 0. If I say Q is equal to 0, then F is equal to, that is QVB sin theta, that is equal to 0. That means if the particle is a neutral particle, then force experienced by that particle, if it is moving with velocity v in a uniform magnetic field, is 0. Okay, case 2. If v is equal to 0, then the charged particle is at rest. हम earlier section में पढ़ी थी that when a charged particle is placed at rest in an uniform magnetic field, no force act on it, or it experiences 0 force. Okay, if v is equal to 0, F is equal to, that is QVB sin theta. If v is equal to 0, then F is equal to 0. So this is proof again that when a charged particle is placed at rest in a uniform magnetic field, it experiences 0 force. Then we will move to case 3. Okay, case 3. In case 3, the charged particle is projected parallel or anti-parallel to the magnetic field. Okay, if it is projected parallel, the charge Q is projected parallel to the magnetic field. In that case, theta is equal to 0. If theta is 0, sin 0 is 0. So I can say F is equal, that is QVB sin 0, or that is equal to 0. So that means when a charged particle is projected parallel to the magnetic field, it experiences 0 force. Let us consider anti-parallel condition. Okay, when the charged particle is projected anti-parallel to the magnetic field, so in that case theta is equal to 180 degree, or sin 180 degree is equal to 0. Okay, so F is equal to, that is QVB sin 180, that is equal to 0. So that means if the charged particle Q is projected anti-parallel to the magnetic field, then also it experiences 0 force. Or you can say, whenever a charged particle is projected either parallel or anti-parallel to the magnetic field, it experiences 0. Okay, case 4. In case 4, the charged particle is projected perpendicular to the magnetic field. When it is projected perpendicular to the magnetic field, theta is equal to 90. Okay, when theta is equal to 90, that is sin 90 is equal to 1, or F is equal to, that is QVB sin 90, that is equal to QVB, or we can say F max is equal to, that is QVB. So that means we can say whenever a charged particle is projected perpendicular to the magnetic field, it experiences maximum force. तो तार डायरेक्शन केमती फाइंड करे तो लेट अस कंसीडर दिस figure. In this figure the magnetic field is inward, the velocity is in this direction, so we can say the velocity is perpendicular to the magnetic field. To find the direction आमे screw rule use करि परिबा ता सहित आमे नेक्स्ट वीडियो रे फ्लेमिंग रूल भी जानिबा ता सहित palm rule भी जानिबा, but we will use a different procedure. So in this procedure, okay, take your right hand, the direction of this finger represents the direction of the velocity of the charged particle. The direction of the palm represents the direction of magnetic field, that is along the direction of the pen, and the thumb represents the direction of force. Again I am saying, take your thumb, the finger represents the direction of finger represents the direction of the motion of the charged particle. The direction of the palm represents the direction of magnetic field, and the thumb represents the magnetic force direction. A figure eta use kariba. Okay, the velocity is this way and the magnetic field is inward. So like this, eta hala velocity direction, magnetic field hoche inward like this. The direction of force will be given by the direction of the thumb. So in this direction. Okay, again author repeat. So let us take your right hand, the direction of this finger represents the direction of motion of the charged particle. The direction of this palm represents the direction of magnetic field, and the direction of this thumb represents the direction of the force. Okay, we will see in the next video.